Welcome to Homework Lib.
We want to find what are going to be the eigenvectors and eigenvalues for the following matrix. So remember that our eigenvalue equation or eigenvector equation is this one, and the matrix A is the value that we get here. Since this matrix is Hermitian, we know that the eigenvalues are going to be real eigenvalues. So to get the eigenvalues, what we need to solve is the determinant of A minus lambda times the identity equal to 0. Remember that this comes from the eigenvector method, and this is going to become the determinant of the matrix lambda 3i minus 3i lambda. So 0 needs to be equal to lambda squared minus 9i squared. Remember that I squared is equal to minus 1. So this is lambda squared minus 9. Therefore, lambda will be equal to plus minus 3. Lambda plus and minus. Those are the two eigenvalues that we have. So now what we need to do is replace these eigenvalues into our eigenvector equation. Recall that my matrix A, 0, 3i, minus 3i, and 0, times my vector, that is going to be the xy vector, is going to be equal to, with the first eigenvector, 3 times x and y. We can also do the same procedure from the A minus lambda times the identity times my vector needs to be equal to 0, which in some cases is going to be a little bit more easy for everyone, right? So for lambda plus, this would become minus 3, 3i, minus 3i, and minus 3 times my vector xy would be equal to 0. So from here we get minus 3x plus 3i times y equal to 0. And at the same time, minus 3i times x minus 3 on y equal to 0. Now the next step is to assume that x is equal to a constant. So we can solve for y. In the first case, we would get that y would be equal to 3 times x divided by 3i. 3 and 3 cancel out. X is equal to a constant, k divided by I, which is equal to minus I times k. This corresponds to the eigenvector the eigenvector, which is a constant times 1 minus I. And its associated eigenvalue is going to be lambda plus equal to 3. Now let's do the same procedure with lambda minus. Let's collect these guys over here. For lambda minus, which is equal to minus 3, the equation now becomes 3i minus 3i, 3 times xy. So this needs to be equal to 0. So from here we get 3x plus 3i and y equal to 0, or the same thing, minus 3ix plus 3y equal to 0. So from here we get that x is going to be equal to minus I times y, or which is the same, we can divide x, or which is the same, we can go ahead and find that y is going to be equal to x divided by minus I, that is equal to I times x. So this is associated to the vector 2, that we're going to call, let's put it already b minus, to associate it with a negative eigenvector, would be equal to a constant times 1 and I. So now we just need to normalize each of the eigenvectors and get the corresponding eigenvalues. And of course, over here, lambda minus would be equal to minus 3. In this case, to normalize b minus, we need to take the dot product. This is going to be equal to 1. And this is going to be equal to 1 plus I squared with a negative sign of it. Remember that whenever we have the inner product, we need to multiply by the complex conjugate of it. And the complex conjugate corresponds to minus I. So this would be, of course, times the constant squared. So this is going to be equal to k squared times 2. So the constant would be equal to 1 over square root of 2. We can do the same thing with the b positive one. B positive dot b positive. This is going to be equal to exactly the same thing, but 1 plus minus I times minus I conjugate, all of this k squared. And for this, also the normalization constant is equal to 1 over square root of 2. So our final result that I'm going to put in black, b positive is going to be equal to 1 over square root of 2 of the vector that we found, that was 1 minus I. And b minus would be 1 over square root of 2 of the vector 1 and I. And the associated lambdas would be lambda positive equal to 3 and lambda negative equal to minus 3. So that would be all. Thank you very much and have a good one.